So I'm going to turn it over to David Montgomery and let him tell you about what he knows.
All right. Candace, thank you. First thing I have to do is see if I can reach the computer. I do have a long enough leash, great. Well, I ought to start by basically saying that I'm a geologist by training. So I'm not a farmer, I'm not a soil scientist. I came to thinking about soils sort of through the side door, through thinking about geologic time. I study what is called geomorphology. It's the processes that actually shape topography, what shapes the nature of the surface of the earth that we walk around on and live on. And I will also start by not making any apology for the title of my book, Dirt. I know very, very well you are not ever supposed to call soil dirt. I was taught this in graduate school in soil science. So what do you expect me to call a book about soil when I then graduate? I'm not that good at following directions. Yes, but essentially, the other thing is that, as we'll come to see, when you look at soils globally, we really have been treating them like dirt for a long time. And if you look at the reason why a geologist like myself would write a book about dirt, about soil, excuse me, is essentially that soil is probably our most strategic resource that we have as a species. It's how we draw our sustenance from the land. And soil degradation is probably what I consider to be the most underappreciated environmental crisis of the 21st century. We talk a lot about what's happening to the atmosphere. People worry about water. But there's an equally pressing, and I think sort of even perhaps more important, long-term trend in the way that people have treated land and how that will affect us in the future. If we look globally at the state of soil degradation around the world, basically that map with all those colors on it, you'll notice there's a lot of red, there's a lot of orange on it. Those are areas where the soil is somewhat degraded in terms of the UN in their assessment, and there's a lot of red all over it. Now, it's a very coarse map, right? You could find farms in any of those really bright red areas where people are actually building soil. But painted with a broad brush, the problem of soil degradation is not a local problem. It's truly a global problem that's been acting out on a global scale. How bad actually is that problem? Well, there's an estimate from about 20 years ago, that's probably still not all that off the mark, that David Pimentel and his colleagues put together, where they basically documented that over the last 40 years, in which in their late 90s, it's basically the time since the Second World War, soil erosion and degradation had caused farmers to abandon about 430 million hectares of arable land. That's an area of land equivalent to about 1/3 of the world's present cropland, which is about an area about the size of India and China combined. In other words, if you think about the problem, as I'll be talking about a little later, of feeding the world later this century, it would actually be awfully handy to have that 1/3 of global cropland that is no longer has its full complement of native soil fertility that we had at about the end of the Second World War. How fast is the loss of global topsoil off of cropland in terms of sort of more concrete units than units the size of India and China? Well, soil erosion in excess of new soil production is on the order of about 23 billion tons per year. Now, anytime you start talking about billions, it's really abstract, right? So what is that? Well, in more concrete terms, that means we're losing a fraction of a percent, about somewhere between 0.5% and 1%, 0.7% if you buy Pimentel's synthesis, of the world's topsoil inventory off of croplands each year. Now, on any given year, that's a small number. Even if he's overestimated it by a factor of 2, though, over the long run, that's a huge number. Because to a geologist like myself, if you basically run those numbers out for a century, well, it would only take about a century and a half at that rate to actually completely plow through our global supply of fertile topsoil. Now, I'm not standing before you arguing that we're going to actually run out of dirt on this planet at some point. Obviously, other things are going to come into play that would influence the rate of topsoil loss. The point I want to make, though, is that the rate that we're losing topsoil now globally is simply not sustainable. And these numbers basically demonstrate it very easily. And you don't even have to think about sustainability over the time frame that a geologist would think of as sustainable, thousands of years. We can demonstrate it's not sustainable over the course of the next century at the pace we're going today. And I'm going to spare you all the historical details of the civilizations that I wrote about in Dirt today, but basically by researching the way that people have treated land and how land has treated people over the last few millennia since we invented agriculture and then led to all this, the subsequent technological developments that allow us to have PowerPoint and projectors and all the other amenities of modern life. There's a very simple fundamental change to the surface of the earth from the invention of the plow that actually changed the balance between soil production and soil erosion, as I'll show you, on a global basis. What is it about the invention of the plow that's sort of the most basic feature of the world's agriculture? Well, essentially, if you leave the ground bare and vulnerable to wind or rain for some part of the year, soil erosion can race ahead of soil production. Soils are built very, very slowly at paces that are on the orders of, say, inches per centuries or millennia, whereas if you can go out on a freshly plowed field, if you have much of a slope to it at all during a decent rainstorm, you can actually lose decades to centuries worth of soil production in an afternoon. That can't actually be sustained, played out over the long run. And what I did in researching dirt is I essentially looked back at the history of many societies, but I'll just show you essentially, I'll pick on our home state for the one that I'll show you today. If you're interested in the story of all the other civilizations and the parallels, get the book, read it. It's I went through as much as I could actually find in the literature and tried to boil it down as concisely as I could and not sacrifice the meaning. So this field it's a winter wheat field over in the Palouse in eastern Washington, taken about 1970. That's about 40 years after the establishment of the Soil Conservation Service, which, as the Icelanders reminded me when I went to give this version of this talk there, was the second Soil Conservation Service established in the world. They beat us by about 50 years. But they also are way ahead of us in terms of topsoil loss, so they got a head start on both. But the reason that a geologist like myself would look at this slide and basically just see soil bleeding off the landscape are all those little channels, those little rills, things you could actually plow over. You can erase them fairly easily. But if they happen consistently, if they happen year after year, how much can it actually add up to over time and over decades or centuries? Vern Kaiser took this photograph back in 1961 that essentially shows another winter wheat field over in the Palouse. The fence line up there on the upper right was a fence line that the farmer put around the water cistern that he used on this field. And the only thing that happened on this field since then, it was plowed as a winter wheat field for 50 years. The orange line at the top shows the land surface in 1911 when the sod was broken. The base of the slope is where my shadow is right there in 1961. It's 50 years. Well, how much of a loss is it? Well, from here to here with my shadow, essentially that increment is a 1 foot increment on a stadia rod. So this shows you 5 feet of soil loss over the course of 50 years. That's about an inch. That's about a foot a decade, inch a year. There's nowhere on this planet that soils form at a pace of an inch a year unless people are doing it directly, intentionally, which I'll get back to later when we get a little more optimistic. But now this is, of course, an extreme example, right? That's why I'm showing it to you. This is the most extreme photograph and example that I can find to make essentially the point that there's a basic problem with what I'll call conventional agriculture, which would be plow-based agriculture, because that convention goes back thousands of years and hundreds of societies. And that basic problem is that if erosion outstrips the rate of soil production, then we're literally mining soil to feed ourselves. And if we depend on soil to feed ourselves, that can only play out for so long. But what you should be sitting there asking yourself is, okay, well, that's like a ridiculously wild example from over in the Palouse. How typical are those kind of rates of erosion on a global basis? And I'll tell you, they are really outrageous. They're really high. So what I tried to do is essentially, after I looked at the history of many civilizations, documented the connections between the way people treated land and how long those societies were able to sustain themselves on the land, I wanted to basically compile what are the rates of erosion that are actually occurring in the modern world. Because if you look back at the archaeological record, you have correlation, you don't have causality. Nobody was out during the fall of the Roman Empire measuring the yield of sediment off of their fields. You can actually back out crop yields through tax records and things like that, but we didn't have geomorphologists in the Greek Empire, in the Mayan Empire, the Roman Empire, all places that literally plowed themselves out of existence. So I basically did something that has become incredibly difficult to get students at UW, or I imagine any other university, to do. And that is actually quite simple. I went to the library and I gathered data. You know, you can't, it's sad but true. It is actually really, you know, the kind of compilation that I did. I spent a couple weeks in the library literally getting all the data I could find on how fast do the world's agricultural fields erode and how fast are soils built. And how fast do the world's landscapes erode naturally under geologic processes. And I pulled all that. I had this 3-week window, and my own students were out in the field gathering their research. I vacuumed up as much as I could, and you know, none of this would probably actually appear on the first few pages of Google when you hit soil erosion. So it doesn't exist in terms of modern research approaches. I did the old-fashioned way. And I found 1,400 studies. Why did I stop at 1,400? I ran out of time. If anyone really has a lot of time on their hands and wants to expand this data set, I've posted all the data that's in this graph online. You can grab it, and I encourage you to build it up and make it publicly available. But what it is you'll notice there's essentially, it's erosion rate across the bottom. Each of these symbols is a study that's documented the rate of topsoil loss or erosion in a landscape. And I did not include any model-based studies. These are all actual observations. The universal soil loss equation as often wildly overpredicts as it underpredicts erosion. I wanted real data. So this is all real stuff. You'll notice that erosion rates on this world vary about over 7 orders of magnitude or so. Down here, that's a 10,000th of a millimeter a year in terms of an erosion rate. And I challenge you to figure out a way to actually measure that. It's really, really hard to measure something that slow. Over here on the right, you're dealing with a centimeter a year, which you actually could go out and measure and observe. There's 4 data sets. The 3 that are actually with the sort of white data points, the triangles are from areas that are cratons. The white data points are geological erosion rates. Think of that as the rate at which a landscape would naturally erode without our assistance. And a craton, does anyone know what a craton is? It's not on the salad. It's a flat, dead part of a continent. It's basically the American Midwest. It's the heart of Australia. It's the Amazon basin, places where tectonic processes are not shoving up mountains. So they're sort of flat areas. They don't have much relief. They're gentle. They erode at rates up to about a millimeter a year. That's still pretty slow. Your fingernails grow a lot faster than that. Soil-mantled terrain, those are areas that are essentially like, I guess, the soil-mantled parts of this island, although the glaciers sort of messed you around a lot. Think the hills of California, Tennessee, places that are not high mountains. They erode at paces up to about a millimeter a year. Alpine and glaciated terrain are the places where you find erosion rates typically above about a millimeter a year or so. By alpine or glaciated, I mean things like the Swiss Alps, I mean the Andes, I mean the Himalaya, the Cascades, although they're at the low end of that erosion rate. But the basic point that I want to make here is that when you compare the data in the black circles, the agriculture data, that's data from conventional plow-based agriculture all around the world. So it's from the huge industrial farms of the American Midwest down to sort of small peasant farms in developing nations. I did not discriminate against methods. I discriminated against whether or not the land was left bare and vulnerable to erosion. And you can draw your own comparison from this graph as to sort of which kind of geological environment modern agriculture most emulates in terms of erosion rates. And we've essentially managed to turn the world's agricultural lands, viewed through this sort of thick lens of a data compilation, into areas that erode like the high Himalaya. We've managed to turn Nebraska and Kansas and Kentucky into places that erode like the high Andes. That's actually a pretty major achievement. It's not necessarily something we ought to be proud of, but it did take some doing. And you can demonstrate with this red line that runs through here that the USDA soil tolerance values, which go from about 0.4 millimeters a year to about a millimeter a year, basically, if you look at modern agriculture up there at the top, most practices around the world through this compilation simply are not sustainable, even if you grant soils forming at the highest rate that they're actually observed to form over the long run. In other words, modern agriculture, the way we practice it, simply is not sustainable any way you cut and slice and dice the data on a global level. This is the most complicated graph that I'll show you. My publisher, by the way, did not want me to actually put XY plots in a book meant for a popular audience because the lore is that you pick that up at Barnes & Noble, you open it, you see a graph, and you put it back down. This is this is the two-axis graph. The last one had one axis, but this is actually the good news graph. And again, I put all the data online, but I had to publish these figures in a scientific journal as opposed to a popular audience book, simply because they had data in them. So it's a percentile plot. Erosion rate is over there on the y-axis, and the two black lines through there are the data that I've already shown you, all combined together. So a percentile plot just shows you what the 50th percentile, so the mean or the median, the average value for which half the data is less, half is higher, would plot right in the middle. So you'd read that by saying, say the conventional agricultural data, these circles, if you want to know the average date, you'd read up into here and then over to the y-axis. And if you want to know the smallest value, would be the first percentile, the largest, the 99th, et cetera. The key point I want to show you here, though, is that there's other data that I've actually introduced. So there's the long-term geological erosion rate data, is that black line running through there. I already said this is the conventional plow-based agriculture. But these other white data points are for the rates of soil production. I vacuumed up all the rates of soil production I could find globally, and that's that white circles. Rates of erosion under native vegetation. Those are the white triangles. You'll notice they plot pretty much on top of the long-term geological erosion rates. You also have erosion rates under conservation agriculture. Low-till, no-till, terraced agriculture. There's agricultural practices that are in other words, there are agricultural practices that can result in soil erosion that are non-discriminable on a global basis from background rates of soil production. In other words, agricultural soil loss is not because humanity farms, but because it arises from how we farm, essentially from using the plow, from leaving the land surface bare and vulnerable to erosion. That's the good news. If I was basically standing here telling you that, well, we're going to farm ourselves out of business no matter what we do, it's like I wouldn't be here. I'd be off drinking somewhere, right? This would be not essentially a very optimistic view. But if you look at this problem that's plagued ancient societies, it actually has a solution. We can grow food intensively. I mean, you people know this. We can grow food intensively in ways that actually both benefit the land and allow us to feed ourselves. If we look at the rates of soil erosion, that same data viewed globally, this is, if you want to see the numbers behind what I was saying, those red numbers up there on top are for conventional agriculture, rates of topsoil loss. You take the median, take the mean, whichever your favorite average is. And from that compilation, you've got somewhere north of 1 millimeter a year. If you look at rates of erosion under no-till agriculture, it's on the order of 1/10 of a millimeter a year. Erosion rates under native vegetation of half of a 1/10 of a millimeter a year. Rates of soil production, again, down near a few percent of a millimeter a year. Long-term geological erosion rate, all those blue numbers, I'm not going to try and argue to you that I can tell the difference between. They're all well below a millimeter a year. What stands out is the red numbers, and not just because I've colored them red. They really are different than long-term rates of soil production or long-term rates of erosion under native vegetation or the rate that the world is eroded or the way that conservation-oriented farmers can actually erode their land. In other words, there can be a balance between long-term soil production and soil erosion, even in agricultural systems, if we apply ourselves to that. If we look at it as a geologist to the big picture view of how fast the world's soils have been eroding, Bruce Wilkinson at the University of Michigan did, I think, the only study I know where someone was audacious enough to try and figure out how fast the continents have been eroding for the last 500 million years since land plants evolved. And what he essentially did is he added up all the world's sedimentary rocks, figured out the areas of the continents they were probably coming from, stacked it back in his mind or in Excel probably back onto the continents, figured out how fast it was bleeding off. And what he came up with is that the average rate of erosion for the last 500 million years is on the order of about 1 inch every 1,400 years. If you look at the average rate of soil erosion at present, it's about 1 inch every 60 years. There's a big difference. We've accelerated that long-term rate of erosion many-fold. The average rate of soil production at present, according to the USDA, which is probably overestimates the rate at which soils form naturally, is on the order of about 1 inch every 500 years. You can take taking these numbers at face value, you can basically argue that for most of the history of life on Earth, since the evolution of land plants, the continents were building soils. The rate of soil production was was faster than the rate of soil loss. Historically, we've reversed those numbers. So we've quite literally gone from a world that was building soil and building life to one in which we're losing soils, degrading soils, and mining life to support our own life. And if you take these numbers, yeah, I've never done this to accompaniment before. I should figure out how to time it better, right? This would be the big reveal when the voice comes in. But essentially, if you take those numbers and you play it out, you can actually predict what the lifespan of an agricultural civilization ought to be, simply from how fast it would take a society to plow through its natural endowment of fertile topsoil. If you look around, and so if you basically take that rate of topsoil loss in the order of 1 millimeter a year or so, erosion of about 1/2 meter to a meter, a 1 to 3 foot thick soil that's typical for most of the world's hillsides, would lead you to predict a lifespan for agricultural plow-based civilizations on the order of 1/2 millennium to a millennium, 500 to 1,000 years. 1,000 years plus or minus a factor of 2. And to a geologist, getting within a factor of 2 is pretty damn precise. It's one of the reasons I like my field. But of course and if you look at the longevity of most major civilizations around the world, it's on the order of 1,000 years, plus or minus 50%. You look at the Greeks, the Romans, the Mayans, the early Chinese society, Easter Island. You can just go right on down the list, as I do in the book, and try and look at that time frame. What are the key exceptions? The key exceptions are civilizations that developed on major river floodplains. Things like the Nile, things like the Tigris and Euphrates, things like the Indus, the big lowland rivers of China. After the Chinese eroded the edge of the Tibetan Plateau, their agriculture moved down into the floodplains, where they sustained it for thousands of years. In other words, the exceptions to the idea of a longevity of civilizations are actually the places that have been subsidized by erosion of the highlands. Ethiopia fed Egypt indirectly until the Aswan Dam was built and everything changed, but I go into that as well. So essentially, I'm not trying to take credit for figuring out that the idea that the way people treat land limits the longevity of civilizations. Plato wrote about this in the 4th century BC. Okay, this is a very old idea. It just keeps getting forgotten over and over again. And Walter Loudermilk wrote a USDA booklet back in the 1950s where he wrote that here in a nutshell, so to speak, we have the underlying hazard of civilization. For by clearing and cultivating sloping land for most of our lands are more or less sloping. We expose soil to accelerated erosion by water and by wind, and in doing this, we enter upon a regime of self-destructive agriculture. Loudermilk basically, he could have blurbed my book 50 years before it was written. In fact, I should have thought of that. My favorite quote along these lines belongs to President Franklin Delano Roosevelt, who in 1937 wrote that a nation that destroys its soils destroys itself. He wrote this in the aftermath of the Dust Bowl, which is the greatest man-made disaster in history. The Dust Bowl was not simply because of a drought. It was because it was the first big drought after the grasses that had held the plains together through 13 previous equivalent droughts in the prior several thousand years had had no impact on the landscape. So it was a man-made disaster. But this all, of course, brings up what I really wanted to emphasize today, because when I wrote Dirt, it was a conscious attempt to look backwards at the history of how people treated land, set up the longevity of societies. Okay, here's the big moment. Yeah, can I have fireworks? Cue, please. But so the question, of course, is soil restoration possible? Can we reverse the historical pattern? Can we pull it out of the fire? Yes! Boom! And the short answer is yes. So they are listening behind the screen. So what would it actually take? It would actually take rebuilding soil. And I actually learned something over the course of writing Dirt. My wife was restoring our yard. We live in North Seattle, sort of in the area between Green Lake and Wallingford. It's an area that had glacial till soil. We had sort of a 6 inches of ratty roots for a lawn when we moved in. When we stripped that lawn off, because my wife wanted to plant a garden, wanted to grow some food, wanted to, just anything but lawn, right? There wasn't a single worm in the soil. It was completely dead stuff. Over the course of about 12 years now, she's completely restored it. We've managed to sequester tons of carbon in trees in the yard and changing the carbon content of our soil. And I basically learned by watching her actually do it in my own yard as I was writing a book about how we've degraded soils around the world. She was restoring the soil in our yard incredibly fast. What would it actually take? Organic matter and labor. Those are two things that we actually have a surplus of in cities. That may not do a lot of good in the agricultural world, but as we'll talk about when we talk about biochar, imagine someday some sort of transportation, call it a train if you want, call it a horse if you're really visionary, coming back out of cities with organic matter in terms of composted material or biochar back to farmland and food coming into the cities, closing the loop, closing the cycle. These are Anne's garden shears. That's the 2 inches of topsoil she made in about 5 years in our lot. It basically looked like this, this khaki tan nasty stuff when we got the place. Where is she? She is working on deadline for something that's due on Monday. She is the soil building expert in the family. I watched her do it and I can write about it. But she's obviously not the first person who's done this. If we look back through history, there were a couple examples that I tabulated in dirt of societies that built soil even as they intensively used land to feed themselves. 2 examples of which here are shown by the Dutch. The Dutch, when they were in the 16th, 17th century, when their population got hemmed in by their neighbors and they kind of had fully farmed their land, we all know how they started building dikes, started reclaiming land from the sea. The part that I didn't fully appreciate was they had a very conscious program of returning urban organic waste to their fields to basically build soils over the course of many decades. It was viewed as a long-term land reclamation project. And you notice here that there's essentially beach sand that they've built. If it was darker, you'd see that's really rich black soil. It's the Plagen soils of Europe. They are the most fertile soils in Europe. People built them, and it only took a few decades. The soils over here on the right, this is a soil pit dug in the Amazon. It's the famous terra preta soil that the indigenous peoples of the Amazon built over thousands of years by adding their cooking fire, charcoal, and their village waste back to the soils in their fields. In other words, and that is the most fertile, rich soil in the Amazon basin. The conventional lores, if you go to essentially the tropics, you're going to find very iron and aluminum-rich soils because all the other nutrients have been leached out of it. When you go around the places that had the highest indigenous population density, you find rich, thick, black earth. So good that it's actually being mined and shipped to the cities in Brazil as potting soil. Yeah, criminal, but they're doing it nonetheless. So the point here, though, is that people actually can build soils while we intensively use them. And why would we bother? Why would somebody like myself essentially make a point of standing up and trying to say that we need to think about trying to restore soils globally? And when I say that, I'm not thinking just simply about restoring soil for growing food. There's actually 4 of the biggest environmental problems that we face this century are problems that would all be partially addressed by restoring soils and restoring carbon to soils in particular. And those are climate change, our ability to feed a post-oil world, to a surprising degree, public health and city livability. I mean, when we talk about restoring soils, I'm not just talking about rural environments. I'm talking about sort of all the space within cities, and even to the extent of trying to plant rooftops and plant spaces that we use in ways that are currently under concrete. And restoring soils globally also is probably one of the few things in light of our rising numbers on this planet that we could do that could actually help secure biodiversity and reverse environmental degradation for the future. One of the other really big environmental crises that we face in the current 6th global extinction. Restoring soil is not going to solve any of those problems. It will help solve all of them. And I can't identify another single thing that actually you could propose as a single action, as perhaps grandiose as it may be, that would help solve all those problems. So let's look at a little more detail. If we look at our current energy situation, for example, we're sitting pretty much at peak oil. This is oil industry data. It's about a decade old. It hasn't changed all that much. The current natural gas boom is going to shift it a little bit and change it a little bit. But the basic issue remains that we're basically approaching the end of the era of very cheap, abundant fossil fuels. Is there anyone in this room who thinks that the price of gasoline in 2100 in real dollars will be less than it is today? Thought I almost had one for a moment. No, nobody ever raises their hand. Once we go over the top of the oil production, it's going to become a scarcer commodity. And if you buy into sort of classical economics, something becomes scarce and it's very useful, the price will go up. So we can forecast, I think, fairly readily that the prices of fossil fuels are going to be going up over the course of the next century. Well, this has implications for how we're going to feed the world for the rest of this century, because for the last half of the last century, our basic strategy for increasing agricultural output was to basically do it through subsidies of nitrogen-based fertilizer and large-scale mechanization, both of which are very fossil fuel intensive. And so this is essentially, from 1961 up through a decade ago. You'll notice the collapse of the Soviet Union influenced fertilizer use globally. But the question I would ask is it really even reasonable to ask the question of whether we could do another green revolution if basically the cost of the primary input to that style of agriculture is projected to go through the roof in the next century? It's a very real question we're not addressing at a global policy level. And why would we need to do that? Well, you've all seen this graph before. The human population is growing, whether it plateaus out at 8 billion, 10 billion, or 12 billion. Take your pick. I wrestle a bit with that number in the last chapter of Dirt. It doesn't change the basic bottom line story that we're going to face a great challenge in feeding the world by the end of this century, simply from the press of our own numbers, and the fact that if we're losing global cropland and topsoil at that pace of a fraction of a percent a year that I talked about, we've got these two numbers working against each other. Our supply of fertile land is going down and our numbers are going up. What this has meant is that the amount of arable land per person is declining. You can see from 61 to 2002, it's fallen by a factor of 2. It's projected to fall again by a factor in half by about 2050, so that we'll have about 0.1 hectares of agricultural land per person on the planet. If we're going to be able to pull that off, we're going to have to farm globally as intensively as the most intensively managed farms on the planet already. Think about that for a minute. And we're going to have to do it in the course of the next century. Or actually, it's 3.5 decades? This is a huge challenge we face. How are we going to, and put simply, how are we going to feed a post-oil world without fertilizer-intensive agriculture? It's a big, big question. And the answer, I think, lies in what I've tried to call a greener revolution. You could call it, I heard someone say the brown revolution a little earlier. I like to think of it as the fifth agricultural revolution. We're starting it. We need to complete it. People in this room are part of the advanced guard in the fifth revolution. But if we look at sort of crop yields from no-till and organic agriculture, they can compete with those with conventional agriculture. Sometimes a little lower in terms of yield, sometimes higher, and often it depends on whether or not you factor in droughts and the potential for future climate in terms of applying that to, say, corn production in the American Midwest. But my contention is that no matter how you look at it, restoring native soil fertility at a global scale is going to be important for sustaining agriculture in a post-oil world. And a post-cheap fertilizer world. Why? Well, we simply need we'll need that native fertility. And the other thing that I learned in looking at dirt is that essentially the rise of popularity in nitrogen, in chemical fertilizers, nitrogen and others, was often due to because of the very degraded state of the lands in Europe and in Eastern North America in the late 19th and early 20th century. You don't get a huge benefit in terms of crop yield from fertilizer application on naturally very fertile land. To me, what that suggests is we need to invest as a species in restoring the fertility of the land so we can actually get off of the very inputs that are projected to be sort of priced out of reach for much of humanity over the next century. So no matter how we look at it, I'd argue we need to think about a greener revolution. But we could also think about restoring soils as an element in trying to manage or mitigate or combat or maybe one day reverse the effects of climate change. By the late 20th century, fully a third of the carbon that had been added to the atmosphere since the Industrial Revolution came from degrading soil organic matter in the American Midwest and in the then Soviet Ukraine and in parts of China. That's a third of the CO2 in the atmosphere came out of the soil, not out of a tailpipe, not out of coal or a chimney or smokestack. And it's my contention that if that much came out of the soil, we can put that much in. In fact, we could probably put a lot more in if we put our minds to it. How would we do it? Well, increasing soil organic matter, like my wife did in our yard, but also through biochar. So let's look for a minute at the sort of global carbon cycle, which we've all sort of seen in one shape or form before. Plants photosynthesize, they bring the organic matter down, roots get into the soil, they die, organic matter gets dropped in the soil, it builds up the soil, the free soil organic carbon reservoir, it gets degraded, and during the degradation of soil organic matter, carbon dioxide is respired back into the atmosphere. And you can think of this as essentially a cycle that has a reservoir in terms of the soil carbon component. But as you grow stuff and if it decays in the soil, you're essentially cycling material through the soil. And the global average residence time of organic matter in soils is on the order of years to decades. It's not terribly long. You can think of it as a very dynamic reservoir at a very broad geologic scale. Now, imagine that if we actually sort of to change rates of input or styles of agriculture. Rattan Lau, a soil scientist, 10 years ago estimated that changes in agricultural practices that increase the sequestration of carbon into the soil, things like no-till agriculture, things like intensive composting, could sequester 0.4 to 1.2 gigatons of carbon per year. Is that a big number? Well, it could offset 10% plus or minus half of global fossil fuel emissions simply by changing agricultural practices globally. Now, that's not going to solve the carbon emissions problem, right? But say we managed to actually reduce our emissions by half by adapting alternative technologies, and we did this, we could be as much as 70-80% of the way towards actually going carbon neutral. Ron Amundsen, a prominent UC Berkeley soil scientist, noted, again about the same time period, that cultivation and deforestation each year releases 4 gigatons of carbon per year, the equivalent of more than half of global fossil fuel emissions. Imagine if we changed global forestry practices as well. In other words, changes in the carbon budget in the soil globally could have a huge impact on the carbon budget in the atmosphere. And for the very simple reason, there's twice as much carbon in the world's soils as there is in the atmosphere. So if we change the proportion, say the percent organic matter in the world's soils, we get a doubling of the amount that we've drawn down in terms of the global carbon concentration in the atmosphere. Now, I mentioned biochar is another way to essentially sequester carbon in the ground. How does it work? Well, it's the low oxygen combustion of organic matter. It's incomplete burning. It's making charcoal, partial burning. And if you look at sort of the natural carbon sequestration by photosynthesis, the plants take carbon out of the atmosphere. Half of it gets respired back into the atmosphere. For the half of the organic matter that ends up in soil carbon, it eventually gets respired back into the atmosphere. It's a closed loop. It's sort of a net no change. Biochar is different. Basically, and why is it different? Carbon is, charcoal, fairly pure carbon, is relatively inert. It breaks down really slowly. And so you can essentially, if you take organic matter and you pyrolyze it, you burn it in a low oxygen environment, basically half of the carbon is bled off, but you can produce energy out of it. And half of it essentially goes into the soil, where its residence time can be on the order of thousands or tens of thousands of years. It depends on how you make it, how finely you grind it, a lot of things. But what do archaeologists use to date those civilizations that I was talking about at the start of the talk? They use charcoal. I mean, we go look for charcoal in the soil, and we can date it up to 50,000 years ago. And the problem is that for even older stuff, for geological applications, the charcoal can still be there. We just can't date it because the radioactive components we rely on to date it decay away even though the charcoal's still there. In other words, you can take carbon out of organic matter, burn it to extract some energy, use it for some other things, whether it's cooking your fire as a peasant farmer in the third world, or the developing world, as I guess we're supposed to call it, and also sequester carbon over the long run. In other words, it's the only carbon negative energy source that we have. And it has the added benefit of it helps boost soil fertility. How does it function? As far as I can tell, I like to think of biochar essentially as microbial hotels, as essentially providing habitat for the microbes that facilitate nutrient flow and transfer in the soil. We're still figuring out how it works, and as a geologist, I'm not the guy figuring that out, but I read the journals. That seems to me to be how it works. What's the potential globally for biochar in this kind of environmental management scenario? Well, global soils have about 1,500 gigatons of carbon in them. The global atmosphere has about half that, 760 gigatons. In other words, the biggest reservoir of carbon that we have direct access to that we can manipulate on this planet is soil. It's not the atmosphere, it's soil. The average residence time for soil organic carbon is less than 2 decades. You measure it in years to a decade or two. But for biochar, it can be far longer than that. The average annual biomass decay, if you just take all the world's biomass that naturally decays, and all the world's forests, grasslands, farms, wherever, it's on the order of 60 gigatons a year. That's roughly 9 or 10 times our global fossil fuel emissions. In other words, as you look at the rate at which nature cycles carbon through the decay and re-photosynthesized process, whatever the right word for that is, nature's spinning a lot faster than we are. We're just bleeding off carbon in the atmosphere at about 1/10 of that rate, but it's a one-way ratchet. We keep doing it. Nature keeps cycling it. What that means, though, is that if we could actually capture 10% of the world's decaying biomass per year and burn it incompletely to make biochar, we could completely offset global fossil fuel emissions. Now, I'm not arguing to you that we should cut down 1/10 of the world's rainforests every year and turn it into biochar. Right? I'm showing you this as an example simply to show you that the potential for actually taking advantage and harvesting the natural annual turnover of biomass to the extent that we can is a way that we can actually capture a carbon negative energy source, boost soil fertility, and it can add up to big numbers. We're not going to completely offset global carbon with it, but it could be a very good down payment and part of a solution to that. In other words, what I'm basically trying to argue to you is that it's time for us to, as a species, to view soil in a completely different way. We need a new view of the soil. That's simply my favorite Einstein quote. We're not going to solve the problems that the hole that we've dug into, we're not going to solve it by continuing digging. So let's look for a minute about how we've tended to look at soils historically. For most of our existence as a species, soils were viewed as a mystery. Fertility was personified, deified. This is Ceres, the Greek goddess of... No, the Ceres was the Roman goddess of cereals, right? Yes. Yes, as you can tell. If you look for most people, for most of our existence since we invented agriculture, and for the 1% of us that are still feeding the rest of us today, soil was a means to a living. Land was to be worked. This is simply to show you how the sort of the basic technology of the plow hasn't changed all that much since the very first image we have of a plow from ancient Sumeria, which is on a clay cylinder seal about the size of my index finger, all the way up through the Middle Ages before the Industrial Revolution. Come the Renaissance, soils started to be viewed as a decipherable mystery. They were something to be studied, something that could be understood, things we could tease apart the mysteries of. Sadly, Leonardo's quote that we know more about the movement of the celestial bodies than about the soil underfoot is as true today as it was 500 years ago. Think about that in the relation of our societal priorities, our scientific priorities over the last 5 centuries in terms of figuring out how the very thing that we depend for our existence upon relative to the farthest objects we can perceive in the night sky. We need to change how we think about soils. How have we been thinking about them for the last couple hundred years? Well, Justus von Liebig kicked off the agrochemical revolution back in the 1843, I think it was, and his philosophy of viewing soil as a chemical medium, a chemical reservoir, a medium to be fertilized as needed, essentially dominated agricultural thinking from the day he proposed it to pretty much today on a global scale. And to be fair, the application of fertilizers has been incredibly useful. It doubled our crop yields in the 20th century. There's a reason people have relied on it, as you all well know, in many circumstances. They work in terms of boosting yields. In the 20th century, soil became viewed as an industrial commodity as mechanization spread to farms around the world. And as soils were started to be viewed as sort of the cheapest input to the agricultural production process, what do you tend to prioritize in any industrial production process? Well, you don't worry about conserving the cheapest of inputs. So as long as the sort of quality and value and even the presence of soil is not monetized in agricultural economics, conservation of soil was not prioritized in agricultural practices. But in the last few decades, the advances in understanding the sort of the biological basis of soil fertility, the biological turnover, the microbial and symbioses between fungi, bacteria, and plants that actually form the basis for natural soil fertility have finally come to be actually understood. Many of the people who started to propose ideas like caring for the mycorrhizae was critical to caring for soils. When Sir Albert Howard proposed that back in the 1930s and 40s, he was ridiculed because he didn't have a mechanism. They didn't understand how it worked. In the last 20 years or so, biologists have started to actually make those connections and unravel those connections and basically vindicate them. The partnerships between soil organisms and plants turn out to be critical to maintaining soil fertility in ways that I think will be very critical for maintaining humanity in a post-oil, a post-cheap fertilizer world. So I'll basically suggest that soil ecology really is the future of agriculture, figuring out how to harness the insights of soil ecology, which boils down often to microbial ecology, which is difficult because you can't see the little buggers, which makes them very hard to study. I think we need to restructure agricultural technology and agriculture to feed the world based on the idea of ecological processes and nutrient cycling. To me, that's the big challenge of this century. And I don't see it really as a question of low-tech organic versus GMO and agrotech. I think that's sort of a slightly misplaced way to put it. I would basically say that the question is how to apply an understanding of soil ecology to the applied problem of increasing and sustaining crop yields in a post-oil environment. So what are those emerging areas of research? Well, how do we get organic matter back into the soil? What's the best way to do it on your farm? What's the best way to do it in these islands relative to Eastern Washington or to Kansas? You know, the answers will be different depending on your place. How much can we get in, how fast? I mean, rates really do matter. What's the role of microbial ecology in soil fertility? Is it the same in all soils? Is it only most important in grassland soils or forest soils? What are the species involved? We're just starting to unlock those answers. And how do we better address linkages between soil and public health? There's very interesting studies that have gone on in cities that have documented that like crime in some urban in inner city neighborhoods goes down when you plant street trees. You know, you put some green space around some projects in inner city areas, and crime rates go down. I mean, there's aspects of social and mental health that are fed by healthy soil in ways that psychologists are just starting to actually document. So can we rebuild soils in cities? How would we do it? I'm actually working with some people to try and figure out that if everyone in Seattle did things like Ann did to our yard and stored the amount of carbon that we have and we cloned that around the city, how much of the city's carbon emissions could we actually offset? It actually turns out to be a non-trivial number. And connections between soil, cities, and public health. As of 2009, more than half of humanity lives in cities. We are officially now an urban species. That's not going to change in the future. So the question of how we can restore urban soils is going to become more and more critical to our own health as individuals and as a society in the future. Things like green space and urban nature, access to that, encouraging physical activity. People want to walk more down a street that has street trees than if there's cars speeding by right next to them. Access to fresh food in cities. There are cities throughout history, scattered throughout history, that grew all their own vegetables in town. Paris in the 19th century grew all their fresh produce in town. Yeah, 3, right? In other words, healthy soil is the foundation upon which public and environmental health is built. It literally starts with the ground beneath your feet. You all know that. But what I want to basically advertise in closing is that healthy soil viewed globally is not going to be a silver bullet for environmental problems, but it could be a secret weapon. It could be humanity's secret weapon. Why is it a secret weapon? Well, it's a secret. We're not talking about using it at a global scale, as a societal scale. But rebuilding soils really could help us address climate change. It could help us feed the world of the future, and it could help improve public health, physical, mental, and social in the urban environments where humanity now dominantly lives and increasingly will do so. In other words, and how would we do that? How would we restore our soils? Well, we got to change how we think about them. The first thing we have to do is we have to stop treating soil like dirt. That's the real message behind the title of the book. And so basically, I'll show you the cover, show you the neat little graphic somebody made for it, and I'll also shamelessly plug my newer book, which is called The Rocks Don't Lie. It's a history of geology and Christianity, how people have looked at the story of Noah's flood and how science and religion cross-pollinated each other over the last few centuries as people argued about that wonderful story and what it means. So I will stop there and thank you for your attention. I did bring copies of books. If anyone would like to get one, feel free to come up and bug me.